This video is an introduction to our work published in CVPR 2025, titled Decoupled Motion Expression Video Segmentation. Referring video object segmentation, or VOS, is a multimodal video task, which aims to segment the target object that is specified by a provided language description across the entire video. Existing RVOS datasets typically consist of videos where the objects are salient and possess distinct and unchanging features. To alleviate this limitation, Motion Expression Video Segmentation, MEVS, is recently proposed, which highlights the importance of the temporal motion characteristics of videos. The new dataset for the task MEVS contains a large number of motion expressions to indicate objects in intricate environments, and one expression may refer to multiple target objects. The current methods designed for traditional RVOS datasets encounter significant performance degradation. Due to the multi-object and inter-frame motion correlation features of the dataset, researchers attempted to inject textual information into the video instance segmentation WIS model to address this new task, as shown in Figure A. Based on WIS model VITA, DCHMP employs mask-2 former to segment possible objects according to static cues, and then designs modules to use motion cues to segment specified objects. However, this framework has several intrinsic issues. Mask-2 Foamer is expected to use static cues to segment as many candidates as possible, but we do not have the ground truth for all objects specified by static cues. For example, DCHMP trains Mask-2 Foamer to first find all the birds, but in reality, only the bird that flies away is supervised. This is inconsistent with the author's motivation to decouple referring video segmentation into static perception and motion perception. In addition, training the entire framework from scratch also leads to higher computational costs. As a result, the question arises how to truly decouple motion expression video segmentation. In this work, we introduced Decoupled Motion Expression Video Segmentation, DMVS, a simple framework constructed on the existing query-based WIS model, emphasizing decoupling the task into video instance segmentation and motion expression understanding. As shown in Figure B, it first uses frozen video instance segmenter to track and segment all candidates, and then recognizes the specified object based on the motion expression, requiring only training the DIS module with fewer parameters. Firstly, we fully utilize object representation output by the WIS model to design our DMVS module. As with previous works, we choose VITA as our video instance segmenter, which accomplishes video-level understanding by associating frame-level object queries. Through VITA, we obtain frame queries that independently represent the object information of each frame and video queries that uniformly represent the entire video. Therefore, we conduct motion expression understanding by associating video queries and frame queries without using spatio-temporal backbone features. To further encode visually enhanced text information, we propose Motion Expression Encoder module. Inspired by DSMP, we decouple motion expressions to static cues and motion cues. The object categories of frame queries mainly come from the category set defined by the WIS dataset. Frame queries interact with static cues to focus on potential candidates of a specified category. Video queries uniformly represent the target object of the entire video clip, including the overall contextual information of the video scene. Video queries interact with motion cues to focus on the target of a specific motion in a category-independent manner. The fusion of sentence embedding with frame queries for static perception and video queries for motion perception completes the final encoding of text information. Due to the lack of additional information, the object queries are mainly initialized randomly in the WIS model. In RVOS, Refer Former first regards the language information as a set of queries. so subsequent reviews methods also follow this paradigm. However, regardless of the method, there is a certain degree of optimization difficulty because there is a significant gap from the final decoded output queries. In an ideal scenario, RVOS essentially selects WE's output based on textual information. Naturally, we propose using video queries to initialize motion queries. We select object queries based on the classification score top K to eliminate the interference of background queries. Finally, motion queries are interactively decoded with enhanced text features to generate masks and classification results. In Table 1, we evaluate the proposed approach DMVS on MeVS dataset. DMVS achieves superior performance compared to other state-of-the-art methods. DMVS achieves 48.6% J and F, 44.2% J, and 52.9% F on MeVS valset, outperforming the leading method DSHMP by 2.2% J and F, 1.2% J, and 3.1% F, respectively. On the MeVS value set, DMVS surpasses DSHMP by a remarkable 3% J and F. We compare our method to previous models on Ref YouTube VOS and Ref Davis 17 datasets in Table 2. On Ref YouTube VS achieves 64.3% J and F, which is 0.7% higher than the previous state-of-the-art DSHMP. On Ref Davis 17, DMVS achieves 65.2% J and F and surpasses DSHMP by 1.2%. These results demonstrate the effectiveness of decoupling motion expression video segmentation into video instance segmentation and motion expression understanding. As shown in Figure 4, we present some visualization results on MeVS. DSHMP does not truly understand motion expressions and tends to segment all instances in the video. On the contrary, DMVS can understand the motion expressions and correctly segment the specified objects. Moreover, the segmentation results have good temporal consistency without errors due to the movement of the objects. The qualitative results further demonstrate the effectiveness of DMVS